Welcome everyone to our YouTube channel where we debug, low-level stuff. Recurrently, PowerPC, Spark, RISC-V and so on. In today's episode, more PS3 PowerPC breakage. For the longest time, aka for some years, I got this oops here that I obviously Instagrammed. On boot, on PS3 and maybe some other systems. BPF, proc alloc, no stats. I looked into the code because initially I actually thought probably the future is now in kernel JIT, just-in-time code generation fails on PS3. So like low memory, 256 megabyte. And one of those codes is super complex stuff, right? Letting me down some rabbit hole here, following the white rabbit. Excuse me. And it turns out, so obviously the first thing I did then, actually you can't just disable that with 10,000 of config options. That is not enough. You can't even just disable that. I had to patch the Linux kernel because I thought like, yeah, I just disable that. For example, JIT by default didn't help. So I looked into the code, actually another scandal by itself. The kernel, the Linux kernel, in many configurations will actually build on each boot JIT networking filter code that I'm really not amused to see. I for years anyway don't like that you can't disable with 10,000 config options. You can't disable to build in network code into the kernel. I would really appreciate if my kernel, my multi-server microkernel, but even the Linux kernel, I would really appreciate if net would be fully modular. 10,000 config options, but net you need to build, at least the core net stuff you need to compile in. Not a fan. Because I would like this like tiny core and modular, and then you could also rm mod and mod probe it and again fix and box it. But anyway, so many modular things. That was, by the way, was it net core PTP classifier? So this code here, this JIT, like this below program BPF ASM. So yeah, that is what's failing. I don't even want that. I don't want net built in. I don't want this PTP classifier here to be built. PTP, yeah. I find it super hilarious, and the crazy thing is, so what I did now is I changed the T2 Linux configuration to not build some obscure config options, avoiding this to be built in. However, that was not the root cause, right? I just did this just because I don't like, was it which kconfig or was it core? Actually, one should be kconfig ptp classify. So actually, you even see net ptp classify is default bool, except if you have some other, like here, for example, network timestamping. Select, so that is net ptp classify. So by default, it is not built in, except if you have network physical timestamping and some other drivers. So I now disabled some other PTP whatever drivers, just because I don't like it, and I probably most of us don't need these drivers, and I don't want my Linux kernel early in the boot to JIT some code. However, that still failed, right? So I thought like, yeah, clearly that is some modern JITting code in the Linux kernel that we don't even want, and on every bird early. Yay, what could possibly go wrong? But then it kept oopsing just at the next occasion. Do I even have that? I don't even have that. So that was only a symptom of that. So then it was, of course, what every sane programmer did. So that didn't help. Then I bisected that further. That is here in our Discord. And so that, as per usual, so yeah, that was BPF, and then I even have that here. So without BPF, it oopsed here in just the next best kernel clone copy process. And then I actually realized that was, actually I thought this was like some null pointer dereference or whatnot, but it turns out no, actually the clue was here. I've seen that for years, but I only now, thanks to your Patreon, YouTube membership and stuff, I finally debugged that. This is actually the real thing here. The real thing is that there is now some checking code for 2 years in the kernel that this system state register, machine state register, MSRR, machine state registers and stuff, are sane. And so that the bisect is insane. So I bisected then the usual stuff, another 2 hours of my weekend gone. And unfortunately, the IBM and their following PowerPC developers, contributing developers here, they broke so much in the way. So what this is this, this bug is visible on PS3, and that's a generic bug, by the way. So that is generic. This is not PS3 specific. It's just showing currently most on PS3. It might also happen. And so like they had to, so what they've done, so 5.12 worked, 5.13, so they broke it with 5.14 like 2 years ago or so. 5.13 is the last good kernel that doesn't have that. So only 7,914 revisions left of roughly in 13 steps or so to bisect. And absolutely golden commits come this way, right? So like, for example, avoid reloading. So the root cause is actually that. I think the root cause is this here. I think because multiple commits on the way don't even boot at all, because they introduced so many, the only constant is change and bugs. Thank you, IBM, for this. Learning, keeping it positive. Thank you so much, IBM and other Linux kernel developers. I learned so much more about PowerPC internals than I ever wanted to learn in this day and age. Certainly helpful for soon writing a whole microkernel. So what they did here is in 2021, in June and summer of 2021, they micro-optimized the kernel. So again, it was working amazingly fine for 20 years of 64-bit PowerPC. But then they decided, let's micro-optimize it. Obviously, hardware is so slow in this PowerPC hardware, obviously so slow, we need to further micro-optimize it. So they avoid here reloading HSRR registers. If they are still valid, when an interrupt is taken, the SRR registers are set to return to where it left off, unless they are modified in the meantime, or the return address on the MSR are modified. There is no need to reload those registers when returning from interrupt. Introduce per CPU flags that track the validity of SRR and HSRR registers. These are cleared when returned from interrupt. When using the registers for something else, for example, Opal calls or the P, they don't write this here, but I add or the P3 hypervisor or other hypervisors. When adjusting the return address or MSR of a context, and when context switching, which changes the return address and MSR. This improves performance of interrupt returns. Yay, amazing. So the problem with that is it clearly doesn't work flawlessly. The next problem is, as I documented here in our Discord, it's like, yeah, thanks kernel developers. Another bisecting, also like, for example, here fixed booting. So the problem is I can't clearly bisect it, but this is most likely the first major commit that break that. Because after this, so this refactoring here is so broken, like this commit is so broken that they needed multiple commits after that, because this commit doesn't even boot. The following commits don't even boot. And then such golden pearls scroll by in your bisect, like fix boot, failure for 4K radix. Radix is the, there are two different types of MMU, the old style PowerPC MMU and the new radix tree MMU, and then also 4K pages, because you can have different page sizes, right, even on 386 and later processors, like huge pages of was 4K, but x86 also in 2 megabyte and even larger gigabyte pages, similar to Spark, as seen recently on our Sunblade. Also here, right, 64K and so on. That is for performance. If you don't need it that fine-grained, larger page sizes, improve performance for less TLB misses and refilling. Also another stuff like fix config if dev typo. It's like, yeah, good luck bisecting your broken IBM PowerPC kernel when like there are only skipped commits left to test. The first bad commit could be any of this. We cannot be sacked more. Yay! So the good thing is now we know what's happening, because I thought from the original, where do I have that here? From the original oops, I thought, shit, eBPF jitting is broken, or shit, the kernel is running out of memory early with initRD still not freed or whatever. So the good news is, this is a warning. This is not a hard, the kernel continued to boot after that. Except all those broken kernels, which don't even boot because broken. Also, you see this here in the Git history, right? I don't make this shit up, you see this here already. So this is the first good commit again. So all the other commits in between are bad because they don't even boot. Also, pro tip to the IBM developers, in the future, if you re-architecture your interrupt handling and other machine state stuff and so on, would be cool if your initial commits, like, can you not git squash this stuff so that, like, each commit boots, because it really sucks to find bugs if your kernel doesn't even freaking boot TM. Just a tiny little bit of recommendation here from our YouTube studio. So this is the first commit, and this commit works again, because this commit is check and fix SRR valid without crashing. So coming full circle, they implemented a micro optimization of not expensively restoring machine-specific registers that come with a hefty penalty of dozens of cycles. Then later figure, shit is breaking randomly, let's check for validity without crashing. Yeah, amazing. I also wonder if they benchmarked how much performance win it still is, because now this commit, of all commits, this was this one, right? 6E. So this commit is checking here check return rex valid, right? So in, by the way, called for interrupt exit user prepare main. So how much of your micro optimization, let's say your micro optimization yielded 1% performance improvement or stuff, or 0.5%, I don't know. I'm not even sure. Actually, I think they didn't include numbers. Save one more register, move interrupt return, avoid reloading, introduce different function. Config if diff typo, thank you very much. Somewhere here. Workaround stack usage, no, not with Cling. Yeah, fix boot failure with 4K radix tree, amazing. There even was the first optimize, implemented memory routines, whatever. I'm pretty sure they didn't include performance figures. They just like, it's where even is the bloody, yeah, among this, yeah, for example here, use interrupt restart table. So there is not a hard performance number, right? I don't think this can be much. Like, this is only optimizing machine state registers. I would be really surprised if this measures then more than 1% or whatever. So for 1%, they broke multiple boot things, and in the end had to implement a check and fix SRR valid without crashing. It's like, have you even benchmarked then if all the refactoring efforts for a performance, 1% performance improvement, I'm guesstimating. So how much is left? 0.5% performance improvement or none at all? Anyway, so I can also show you, like, you obviously can 6E, this is this one here. So yeah, I showed you that. So that is then checking the state, right? So they have, like with all the refactoring, they now have SRR0 and 1, and they log this once. The other stuff, like you see already here, that, for example, when they introduce that, so like they start to refactor, for example here, avoid reloading HSRR registers if they are still valid. The problem with this commits already don't boot for me, right? So like, and also obviously it's like move interrupt vector, interrupt return ASM to interrupt, 64 ASM, then system call avoid setting stuff. It's like, yeah, like I understand like refactoring like this this small piece and then this small piece, but yeah, helps little if it doesn't boot anymore, right? So like, yeah, cool. The whole pack of a dozen commits is broken, except maybe on some IBM servers that I don't have, some variant of whatever. I didn't test this on the G5, I can't be exact. Anyway, so you also see already that they had to fix multiple things, right? For example, here, interrupt soft enable race fix, treat low kernel as IRQ soft and mask for whatever reason. Then use interrupt restart table to, so this is the main speed up thing. Then rename slightly change, it's like, yeah, whatever, doesn't. Refactor exit users, like, yeah, whatever. Introduce prep IRQ for whatever. Refactors. There were multiple fixes, like including check fix for SRR, but they also had their fix config typo and save one more register, mask interrupt handler, free one more register, take advantage of that cleansing, whatever. So the good news is it's only a warning, and we kinda could ignore it, like I ignored for 2 years. It's certainly good to know, because so often, like yesterday, for 6 months, I knew PS3 was not even booting anymore. So like nothing like 2 years later. I only wanted to finally solve this thing here, not to have totally degrading PS3 support that sooner or later the new kernel developers will decide to delete, because nobody except ourselves is fixing this shit anymore. And also understand what's going on and hopefully solve this. So the way to really solve it. So the problem is, this is really complex stuff, as you see here. You can also see his original commit of that one here. Did I have, can also get diff. So what to do now, right? So the problem is that's complex shit, that's complexly broken. Here config, so this is now here, new syscall exit restart, interrupt exit user restart, exit kernel restart. Then here, new code for that, always prep IRQ for kernel, enable exit, and okay, moving the stuff around here, and syscall stuff and bits, and stack store exit can be restarted because interrupt stack frame might have been clobbered, and stuff, and like complex stuff going on in assembly. The usual stuff that we love and certainly love to guru meditate here in our spare time. So yes, this is complex stuff, right? Like complex micro optimization for 1% more performance. And what they also do here in other, so I'm not even sure if this commit works, because only in later commits they actually also fix their opal calls here. Where was it? So use interrupt restart. Rename, slightly change, refactor. Where was opal? Or was it in? Oh wait, this was 5.9. This was another commit. 5.9. 5.9. Avoid. Is it this one? Did I wait? 5. Oh no, these are. All right, these are 2 commits even. And yeah, I wonder, because as you see, some of the commits here are before and after. I wonder if all of them even boot on IBM servers. Like if you have some, I have some Power 8, but I'm not feeling like rebooting my Power 8 server like a dozen times now to B6. This nonsense. So that is that here, by the way. So that is the original Meha SRRM. I just saw it here somewhere. Where was it? Here, SRR valid and HS. So this is SRR Rex clobbered. New functions here for this micro optimization. Here, including a new 8 valid for those. Modifying micro optimizing, modifying stuff all over the kernel. Of totally easy to read and understand assembly, obviously. So this is how micro optimizations look like, right? Instead of just setting here some bits using, so this is using these functions to set this valid bit, right? So that probably sets not valid or whatever. Okay, this is also not the function. Yeah, so this clears this valid to 0. So either this sets the saved MSR machine state register, or clears also this valid things here for later to whether in interrupt handler or other task switching to set this here. So the real fix, and I probably should read the comments, which we have quite some. So the real fix for that is would find out. Also, I wanted to show you Opal. So Opal is IBM firmware here for Power NV. I believe, as far as I remember, NV was not virtualized, in contrast to PowerPC virtualized. Opal here for firmware call or whatever. IBM Opal was some open. What was Power Abstraction Layer here? Open Power Abstraction Layer. And for that firmware. So what they do here is Opal core firmware may use SRR and or HSRR. And I believe, according to my hour-long analysis here on this beautiful winter Sunday, is that we need something similar for PS3 hypervisor calls, or at least somewhere in the boot chain. In 3 hours of my Sunday time, I've not yet figured the correct places for that out. So it would be logical that if we call into the hypervisor, the LV1 hypervisor, that I believe was even also co-developed with IBM also clobbers SRR and or HSR. So we probably simply need some SRRX clobbered at the right functions, similar to Opal call here, just that we have a couple of hypervisor calls. The problem is we have hypervisor calls all over the place, so we actually would need, I don't know, I mean, we could continue, like the next step would be to include this in all hypervisor calls and find out if this affects all hypervisor calls or not. So yeah, something like that we would need. As usual, shall I subscribe for supporting my work here of fixing behind IBM's 64-bit PowerPC micro optimizations. Maybe we should actually debug, not debug, maybe we should actually benchmark how much performance improvements this gives us, if any. And also a pro tip for future IBM developers watching this video. Not only would be cool if your commits, especially, I mean, I understand if I have my local Git tree, that not all commits work, but if you send it off to Linux kernel developer stuff, architecture, maintainer, then like maybe you can squash your commits so that you have a set of booting commits and not like a set of non-booting commits. And if you improve performance, maybe include some performance figures of what you benchmarked and how much a single-digit % it was faster for us to even know what we should double check that your amazing micro optimization actually is faster, and the future checks here, SRR valid checks, did eat all your initial performance improvements. Anyway, I also wonder if you could get slightly higher performance, like if the kernel code is over 2 years later, would finally find all places that still clobber these registers, machine state registers. If we can disable that, because currently that is hard enabled. So you probably could get a tiny little bit extra percentage disabling this check, which currently is hard enabled for all book 3S 64-bit PowerPC. Anyway, basically you could probably even so yeah, basically, I mean, yeah, you could simply, but you could make this a, the funny thing is, like, if you have anything else in PowerPC book 3S, you have the overhead of calling an empty function, right? Which is somehow I would say, I mean, you would need, is it one file, or to optimize away? Okay, it is one file, so okay, you would hope a modern compiler is clever enough to optimize the empty function callback. Anyway, yeah. that is that. In another day of a life of a Linux kernel developer. And of course, the recurrent criticism of the only constant is change and regressions. Another case 666 of the only constant is change and regressions. More changes, more regressions, and was this micro-optimization really worth it? Leave in the comments below. Let's take a look at the comments of all the people tuning in live here. So many comments, tons of companies in the US use IBM but never touch Linux. You would be surprised nowadays. Basically everything mission critical is soon running Linux. So presume you treat the PS3 cell just as a dual core and ignore the SPE. Why would we? We run SIMD, single instruction multiple data, streaming multimedia stuff on there, like you would do. Why would we treat that as a dual core? We would waste all the billions of mega flops of performance things. There is not much software for the SPUs, unfortunately. Why? You can just compile your own. And yeah, we should do more. You can choose GCC and bin utils and stuff. But yeah. Garfield wrote there, far as they know, the SPUs were meant to run shaders with the NVIDIA RSX, not intended to be designed as GPU. That is not true as far as I know. Initially, the PS3 was actually designed by Sony without the NVIDIA RSX. Initially, the cell was designed exactly for that. Similar to Intel Larabi, other similar projects. The SPEs were meant to be the GPU only when Sony found that performance wasn't high enough and that was too difficult to program. They additionally added the RSX. So my understanding, the NVIDIA RSX is somewhat of an afterthought and only adding more graphic compute performance and making it easier for game developers is my understanding. But if you are a Sony designer or have other inside knowledge, please correct me in the comments below. SPE used to run many things: encoding, scaling, physics, tracing. Yeah, exactly. You can run anything. It is even used for Blu-ray acceleration. For, as far as I know, it's even used for Super Audio CD decrypting. So what Sony has done, Sony has in often cases, as far as I found and remember, offloaded some decryption and decoding on the SPEs, not only to improve performance, but often also to simply obfuscate some decrypting and stuff, right? Like Super Audio CD and other such stuff. More comments. SPEs have been used FFmpeg in the past. Decode H.264. To know if that code's still available though. Yeah, I've not checked, but we will get back to SPE stuff. I packaged the actually, is it GCC? Yeah, I think you can use GCC here. I packaged all this stuff, GCC bin utils in T2. It was mostly working the last time I checked, but there was, I think everything worked except some DMA notifiers that I didn't yet had the mood to. I mean, there's so much else broken, right? Like as you see, every quarter, the upstream Linux kernel developers break something, right? Sunblade 1000, SCSI broken, SGIO2 frame buffer broken, 32-bit Spark frame buffer broken, PS3 storage broken, previous video, like data corruption because they can't handle offsets, like whatever they touch they break. PS3 storage was broken, this is broken. It's like, yeah, basically I burn all my time of keeping the stuff alive instead of doing the nice things, but actually my plan was to actually also showcase SPE programming. Garfield writes, did you not first write what you write, SPEs were meant to run shaders with the NVIDIA and not? First you write, somehow you contradict yourself, no? They added the GPU to the design once they learned the Xbox 360 used AMD GPUs in the same chip package. Somehow you, I don't know. Anyway, but at least it's partially confirms what I said, that initially this was not, NVIDIA RSX was not part of the design. Maybe some more comments, these MSRs and CX optimization about higher CX, which original hardware could probably not run, thinking thousands of run. Hard to unlock the abilities of the PS3 due to a wonky architecture. This is not a wonky architecture, it's actually, this is not a wonky architecture, it is a extremely forward-looking architecture, just to what we see today with GPUs, entirely flexible, programmable shaders and AI acceleration. I wish also Intel has done something similar with Larrabee, which was not as successful as Intel always over designs their stuff. It is not unlike entirely flexible programming stuff. It was forward-looking in seeing graphics and other AI stuff has massively parallel stuff and having that general purpose programmable. Certainly hindered by process and integration and stuff. I have the improved cell, right? IBM Power X, previous videos. I have this PCI accelerator. I wish IBM had further scaled it down and scaled it up for, I think, 512 SPE-based GPU things from IBM instead of NVIDIA's. Like, just look at the also power hungriness. Like, people whine, but the P3 consumes electricity. Yeah, first of all, this is 20-year-old process stuff, and second of all, look on your latest and greatest NVIDIA. Imagine IBM and Sony would have shrunk that a couple of times more and put 512 or just 128 of those in one chip. So I don't call it wonky, it's just more difficult, but it's not more difficult. This is also people complaining, but the SPs are so difficult to program. Not really. Your NVIDIA GPU is also difficult to program because you need to dedicatedly handle that with Spear 5 shaders and stuff, right? Or other NVIDIA CUDA. It's not unlike NVIDIA CUDA. It's as difficult or not difficult as other NVIDIA game programming and AI and stuff. Anyway. Reminds me, Sega Saturn and its 2 GPUs. Yeah, a lot of, I mean, this is any coprocessor, right? Even the next Cube had a Motorola DSP 6556K. The SGO2 had a MIPS coprocessor and so on, right? Other stuff. So what do we have there? Had a dual G5, not the water cooling. They are all dead. Not sure what do you mean with all dead. My dual core G5 is fine. And the water-cooled model is also not all dead. A friend kernel developer of mine just some years ago got a quad-core G5. Although, ironically, he didn't even know it's water-cooled. Like, a friend of mine, a friend kernel developer of mine, hey, I finally got a quad-core G5, and I immediately, hey, did it not yet leak? And he's like, what do you mean with leak? It's like, yeah, they're water cooled, right? What? They were water cooled. So first thing they did was open it actually. So yeah, so much too. Anyway, Sega Saturn stuff. What else do you have there? How much? So yeah, quite some stuff going on. Which article shows grub? Did I do something wrong? Grub, whatever, FreeBSD. All you can see it on old Gleek kernels in the GNU symbols. Even the PS3 uses FreeBSD, OpenBSD code. GNU symbols, not FreeBSD, where most of the kernel exploit FreeBSD based. Yeah. Yeah, the kernel is FreeBSD, but of course closed, right? BSD license, they just keep it closed. So I totally agree. As far as I know, the kernel is mostly FreeBSD with, of course, their modifications. And it's closed because BSD license does not require them to release the sources. Anyway, so yeah, what we need to do next is, so that's the issue. Thankfully, it works. I also committed other stuff today. So next, we would need to find out here our hypervisor call stuff. Maybe we continue. Basically, we can move over to Twitch and theoretically debug that another 30 minutes also live. That's basically the summary. It is, I'm shocked but it doesn't surprise me anymore. And we urgently, it is my opinion since a decade already, or nearly two, for nearly 2 decades, my opinion was we need a better kernel than the Linux kernel. Unfortunately, the Linux kernel is nearly the best we have, the BSDs in my opinion. Less features, less good and stuff. In the Linux kernel, the most annoying thing is the only constant is change and regressions, and that it is a single address space, monolithic and stuff, and even the network core is built in. But that's a topic for another video. That is a summary for today. Another sad day of dissecting the kernel, especially with all the gazillions of not even booting kernels in between. I hope you enjoyed and learned something. Don't forget to finance all this work with some Patreon and YouTube membership. Let's go over to Twitch and take a look at the P3 hypervisor calls, and if we find something obvious in another 30 or so minutes that we can attribute with this MSRR register clobbered functions. I hope you enjoyed this and learned something, whether it's low-level kernel micro-optimization or P3 gossip. And I hope to see you soon for all the next fun stuff or going over to Twitch to come.